Today we are going to talk about sodium-potassium pump. We also call them sodium-potassium ATPases, right? We'll start our lecture in a sequence, right? First of all, I will give a brief introduction. Then we will talk about the structure of this pump. And once we have done with the structure, we'll talk about its function, that how this pump works and what are the different steps while it is operating. And after that, how this pump is regulated. And in the end, we'll talk about the most important thing. What is the role of this pump in our body? What are biological functions? What is physiological and pharmacological importance? For example, what is the role of this pump in cell volume regulation? Role of this pump in excitable tissues and especially in resting membrane potential generation. Then role of this pump in secondary active transport mechanism in the body. And recently we are discovering that sodium-potassium ATPases are also playing role as signal transducers. And in the end of the lecture, we will talk about digitalis or digoxin and digitoxin, these drugs, cardiac glycosides, how they work on the sodium-potassium pump, and eventually these drugs leads to positive inotropic action or increased contractility of myocardial cells. So first of all, we'll start with introduction, right? First of all, I would love to tell you that sodium-potassium pumps are present in all animal cells, right? Sodium-potassium pumps are present in all animal cells, and where they are present? These pumps are basically present in the cell membranes, right? These pumps are present in the cell membrane. And what is the basic function of it? Before that, let's suppose this is a pump, sodium-potassium pump, and this sodium-potassium pump is a transmembrane complex of proteins. What is it? This basically a protein, and this protein is transmembrane, right? And what are its important functions, right? Basically, this pump is doing sodium expulsion. What it is doing? During one pump cycle, right, it expels free sodium from the cell, from inside of the cell to the outside of the cell, right? And when it pumps free sodium ions out of the cell, it also imports two potassium ions inside the cell, right? So we can say this pump is basically a transport protein. It is basically a transport protein. Why we call it a transport protein? Because it is transporting sodium from inside the cell to the outside the cell and transporting potassium from outside the cell to the inside the cell. And this function it performs by using energy derived from ATP. It derives energy from ATP, adenosine triphosphate, and of course then it breaks down adenosine triphosphate into ADP and inorganic phosphate. So now we can see that this protein not only acting as a transporter to transport the sodium out of the cells and transport the potassium to inside the cell, but it is also working as an enzyme. It is also working as an enzyme because this is able to break down the ATP. Within this protein, there is a special domain, and that domain has capability to break down the ATP and derive energy, right, by breaking the ATP into ADP and phosphate. Now, due to this reason that it has the ability to break down the ATP, we also call this ATPase. We also call it ATPase. So we can say that this can be called sodium-potassium pump, right? And it can also be called sodium potassium ATPase. Is that right? So again, I will repeat it. What is the basic function of this pump? Basic function of this pump is that this pump is expelling sodium out of the cells and bringing potassium into the cells, and all our cells due to the function of this pump are accumulating potassium. It means our cells are the bags of potassium. Our cells are bags of potassium due to the function of this pump. Cells may have hundreds or thousands of the pump in their membrane, and some cells like neurons and myocardial cells and muscle cells, there are millions of pumps in their membrane. So what these pumps are doing? They are accumulating the potassium inside, they are throwing the sodium outside. So cells are becoming the bags of potassium surrounded by extracellular fluid which is rich in sodium. Cells are, due to the functions of these pumps, right? Cells are bags of potassium surrounded by extracellular fluid rich in sodium. Is that right? And it's very important concept that cells are the bags of potassium. It's clinically very important, because if there's a massive destruction of cells in your body, lot of potassium will come in extracellular fluid and it will produce hyperkalemia. If there is massive destruction of cells in your body, that may release lot of potassium from intracellular compartments to the extracellular compartment, and that may produce hyperkalemia. And that hyperkalemia can lead to cardiac arrhythmias or even death. That can be fatal. Again, I want my students to remember, cells are the bag of potassium, and primary role played by sodium-potassium ATPases, which are accumulating potassium into cells. And whenever there is massive destruction of cells, that may lead to hyperkalemia. For example, crash injuries, right? Extensive surgeries, burns, hemolysis, septicemia and destruction of tissues, tumor lysis syndrome, when a lot of tumor cells undergo lysis. So what I'm talking about, sodium-potassium ATPases are responsible to throw the sodium out of cells. Sodiums are just like men's, and potassium is like, yes, women. Okay, make it a little age group down. All of you are so beautiful. So I should mention sodium is like boys and potassium is like girls. So these pumps are constantly pumping the boys out of the cells and bringing the girls into cells. The cells are rich in, not rich in girls, rich in potassium. Is that right? Surrounded by, don't tell me boys, sodium rich fluid. Is that right? Now, you know, this pump in our body uses a lot of energy. Up to 20 to 25% of energy produced in our body is utilized by this pump. And in central nervous system, up to 60-70%, the major chunk of energy produced in your central nervous system is utilized by this pump. It means this pump must be doing very, very important things, right? We'll talk about those important things later. First of all, I will go to the structure of this pump. Right? That how exactly it works. Okay. Let me extend this cell membrane, and this picture I'm going to enlarge it. Basically, this pump consists of two proteins, right? There is alpha component of the protein and there is beta component of the protein. So we can say this pump is basically made of two globular proteins. This is made of two globular proteins, and these globular proteins are called alpha proteins and beta proteins. These alpha proteins right? These alpha proteins are larger in size and beta component is smaller in size, right? This alpha component is larger, right? And it is about 100,000 kilodaltons. Its molecular weight is 100,000, and this is smaller, like 55,000. But what is really important to remember that this pump, sodium potassium ATPases, are basically made of two globular proteins, right? Alpha and beta. We can say these pumps are just heterodimeric pump. Heterodimeric pump. Out of these two units, alpha unit is the real action unit, the big man. Alpha unit is the big man. And beta unit is the small one, baby man, right? Function of beta unit is really not so detailed learned, but about alpha we know a lot, right? As I mentioned, that if we talk about the alpha unit, first of all, it has a molecular weight around 100,000. Number two, it's membrane spanning. It is membrane spanning. And how many times alpha unit spans through the membrane? About 10 times. It passes through the membrane, alpha unit, 10 times. I will make it here. Alpha unit 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we can say this alpha unit is basically a large protein, globular protein, right, which has 10 transmembrane peptide chain, or it has a long peptide chain which 10 times passes through the membrane, or we can say it is 10 pass protein. 10 pass transmembrane protein, and its amino end of this protein peptide and its carboxyl end both are intracellular. So this is your alpha subunit. This is your alpha subunit. Beta subunit, that is smaller, that is only one pass. It passes only once through the membrane, right? So it is 100,000 and beta is 55,000. Okay, we'll write it here. It is 100,000 molecular weight, and here it is 50,000, 55,000, 55,000. It's really not that important. If you just remember, alpha unit is larger and beta unit is smaller is enough, right? Now, the function of the beta unit is very simple. Function of the beta subunit is very simple. Basically, during the ribosomal action, when alpha and beta units or peptides are being produced and they enter into endoplasmic reticulum, and then they pass through the Golgi apparatus and eventually they are inserted into membrane, during all that process of protein synthesis and folding and targeting and anchoring of protein or pump into the membrane, it is the role of the beta. It is the role of the beta that it helps in the folding of the alpha, it helps in the transport of the alpha, targeting of alpha unit to the membrane, and also it helps the alpha unit to remain anchored in the membrane. I will repeat. Beta unit has very simple function, right? Beta unit is basically assisting the folding, targeting and anchoring of alpha unit in the membrane, right? That's done with it. But what is the importance of alpha? The real pump, the real enzyme is alpha unit. The real protein in this pump, sodium potassium ATPase, as I said, this is made of two components, but the real pump action, the real transport action is done by alpha unit. Even the real transport of sodium out and bringing potassium in is done by alpha. And the real breakdown of ATP, the enzyme action, is also done by alpha. Is that right? So now onward, after this basic structure, let's compare and contrast. First of all, structure, yes, sodium potassium pump, they are present in all animal cells membrane. Done. Number two, they are made of, what they are doing, they are expelling during one pump cycle, they are exporting 3 sodium out of the cell and bringing 2 potassium into the cell while using the energy derived from ATP, right? Because this pump is transporting the, what is this, ions, so we can say this is ion transporter. This is ion transporter. And because normally sodium is very high in extracellular fluid, normally sodium level is high in extracellular fluid. What is the level of sodium outside? Yes, sodium levels is equal to about 140 milli equivalent per liter, right? Inside sodium is very less, outside sodium is high, and still this pump is pumping the sodium against the concentration gradient, so it must be active transport. Those transporter proteins which transfer the substances against their concentration gradient, they are considered active transporters. So sodium potassium pump, while it is pumping the sodium from inside to the outside, it is actually pumping the sodium from lower concentration of intracellular environment to the higher concentration of sodium extracellular environment. So basically it is pumping the sodium against the concentration gradient. So this is considered a active transport. Here I would love to mention one more thing. Not only it is pumping the sodium against the concentration gradient, this pump is also pumping the sodium against the electrical gradient, because I will explain it later that normally cells interior are electronegative, resting membrane potential. I will explain it later. But because normally cells membrane's interior side is electronegative, so due to the resting membrane potential, and this pump is pumping the sodium against the electrical gradient also, because electronegativity would love to hold the sodium in, but this pump forcefully pumps the sodium out. So this pump is pumping against the chemical concentration gradient and also pumping against the electrical gradient when it pumps sodium out. So we can say that this pump is pumping the sodium ions during one pump action, 3 sodium ions against the electrochemical gradient. The word we use it, it's pumping the sodium out of the cell against electrochemical gradient. Is that right? And about potassium, it is pumping the potassium also against the concentration gradient, because it is pumping the potassium from extracellular environment which has low potassium to the intracellular environment which has high potassium. So we can say it is pumping the potassium also against the concentration gradient. As you know, the potassium outside is around 4 milli equivalent per liter, and inside it is a lot more. So what we can say now, that this pump is transporting sodium against the electrochemical gradient and outside, and it is bringing the potassium against the concentration gradient inside. So as far as sodium and potassium is concerned, this pump is an example of active transporter. It is an active transporter. And from where the energy is derived from active transport, when you are pumping the substances against the concentration gradient or against the electrochemical gradient, you need to have energy. It is just like that if you have to take a object uphill. Actually sodium is being pumped out uphill and potassium is being pumped in uphill, right? So we need energy. Because this pump utilizes energy directly, because this pump is using direct metabolic energy stored in ATP, so we say This is primary active transporter. Again, what is primary active transporter? I told you active transporter is any pump which is pumping the substances against electrochemical gradient, right? That is active transporter. But if active transporter is using metabolic energy directly by itself, then it is primary active transporter. Secondary active transporter I will teach later. So we can say now sodium potassium ATPases are primary active transporter of sodium, 3 sodium outward and 2 potassium inward. Is that right? While using metabolic energy derived from ATP. Here one more thing which I would love to mention, that when 3 sodiums are going out, we say 3 cations, positive charges are moving out. And when 3 sodium goes out, at the same time 2 potassium comes in, right? And this is not 4 potassium, this is 4 milli. Potassium levels in the blood are around 4 milli equivalent. Actually, there is a range of about 3.5 millimole up to 6.5 millimole, less than 3.5 millimole or milli equivalent per liter. We say there is a hypokalemia, and more than 6.5 milli equivalent per liter, it is said to be hyperkalemia. But actually potassium were 2. There were 2 potassium. Now, one more important point to note here is 3 sodiums are going out and 2 potassium are brought in. It means 3 positive charges are replaced with 2 positive charges. So during one pump cycle, actually interior of the membrane is losing 1 cation. During one pump cycle, because 3 positive charges go out and 2 positive charges come in, so during one pump cycle, 1 cation is lost from interior side of the membrane. So as compared to the outer side of the membrane, in interior side of the membrane has less cations due to action of this pump. Again I will repeat. For example, you have 1 million pumps in a membrane. You have 1 million pumps in a membrane, and all of them move only once. All of them move only once. 3 million sodiums will go out, but only 2 million potassium will come in. So more cations are moving out, less cations are coming in. So interior of the membrane will be slightly deficient in positive charges as compared to the outside. Or if we consider outside neutral, then inside is deficient in positive charges, or we can say it is slightly negative. It means when these pumps are working, they are creating electrical potential difference outside and inside, right? A small electrical differences, but this small electrical difference is not the resting membrane potential. That I will explain later. But when these pumps are moving, because more cations are pumped out and less cations are brought in, so interior of the membrane becomes slightly negative as compared to the exterior of the membrane. So we say that these pumps, when they are functioning, they are producing the potential differences. So we say these pumps are electrogenic pumps. These are electrogenic pump. So up to now, we can say sodium potassium ATPases are present in the membranes, plasma membranes. They are primary active transporters for movement of the sodium and the potassium. Is that right? Sodium is expelled out and potassium is brought in, but more sodium is going out and less potassium is coming in. So balance of the ion is disturbed, and that lead to a little potential across the membrane, and that is called that this pump is basically electrogenic pump. Right? Any question up to this? And again repeat, alpha unit is bigger and beta unit is smaller. Main purpose of smaller beta unit is that it helps in folding, yes, folding, targeting and anchoring of alpha unit in the membrane. The real action is in alpha unit. It's a larger unit, and this is the unit which is doing the transport function for sodium, and also transport function for potassium, and also handling the ATP, ADP and phosphates. So we can say that this alpha unit, not only it is larger, it must have pump action, and because it is a transporter, so it it should have sodium binding sites, sodium binding sites internally, and it should have, yes, potassium binding sites externally. I will go into detail of that. And also it must have a site where it binds ATP, and it must have a site where it binds inorganic phosphates. So what we can say, that this pump should have multiple domains. There should be sodium binding domain, there should be potassium binding domain, there should be ATP binding domain, and there should be an enzyme domain which is called ATPase domain. There should be an ATPase domain. It should be able to bind ATP, then it should be able to break the ATP by which domain? ATPase domain, and after that, after breaking the ATP, it releases the ADP, but hold the phosphate with it. Holds the phosphate with it, because it has a very special point for phosphate binding. And when phosphate is bound with this pump, we say pump is phosphorylated. What we say? Pump is phosphorylated. This pump really works when it gets phosphorylated. This pump really works when it gets phosphorylated. That is why this pump is also called P-type. P-type pumps. P-type pumps. What are P-type pumps? P does not stand for anything else here. I'm strictly speaking, here it stands only for phosphate. So those pumps which only operate when they break down the ATP into ADP and phosphate and hold the what? Phosphate with them, and only then they are functional when they are phosphorylated. Such pumps are called P-type pumps, right? So we have learned about basics about it, we have learned about its structure, right? Now I will go to how this pump functions. What are the different steps during expulsion of the 3 sodium and bringing in the 2 potassium and breakdown of the ATP. Right now we are moving to this component of the lecture, that is the function of the pump. For this purpose, I will make the detailed model of working model of this structure right after the break. Now in this section of the video lecture, we are going to talk about how sodium potassium pump or sodium potassium ATPases work, how they function, what are the different steps in which they transport the sodium out, bring the potassium in, and how they break down the ATP and undergo phosphorylation and dephosphorylation process. So let's start step by step. I'm going to talk about which unit? Beta unit, alpha unit? Alpha unit. As you remember, alpha unit is basically active transporter as well as having ATPase function. And I mentioned that alpha unit has the binding sites for sodium, for potassium, for ATP, and also has ability to bind inorganic phosphate, and of course has an enzymatic unit which is called ATPase unit, right? So let's go into detail. We are going to make a sort of model how it works, right? Let's suppose that here is the pump at 0 position. This is pump present in the membrane and it is at its 0 position. Before really it start action, the first thing what should it do? If you are going to use any pump, first of all you have to put the power. Is that right? So the very first function of this pump is that it will bind ATP. The very first function is that it will bind ATP, and when it binds ATP, let's suppose this is the point, this is the hook where ATP binds, right? I'm putting here one phosphate, then another phosphate, then another phosphate, and then adenosine, right? Now this is ATP. Now this enzyme or this transporter, this basically exists in two configurations or two conformation. This conformation in which its mouth is open inside, it is called E1. What state? E1 state. So this is E1 state loaded with ATP. So we will say this is E1 plus ATP state. This is step number 1. This pump will, as you are going in your car, first of all you have to put the petrol. Is that right? So it is doing its first function. What is that? Binding the ATP. Once it has bound the energy rich molecule with it, the next type is just like car. What you will do? You will sit in the car. But here you are not going to sit in the car. Who is going to sit in the car? Sodium. The next point is that it has to take the boils from inside and throw them out. So there should be, in next step, what will happen, that this pump is from step number 1, it's going to the step number 2. You already know that in step number 1, it was having what? ATP, but this time, once it is loaded with ATP, there are special pockets in which sodium can sit in, right? Those pockets will open. There are special pockets in which sodium will sit. Now, this is pocket number 1, pocket number 2, pocket number 3. These are the pockets which will bind sodium. These are sodium binding domains. What are these? These are sodium binding domain. They were originally present over here, but they were in low affinity state. They were in low affinity state, low binding state. Once ATP is bind and it is present in E1 state, right, its sodium binding domains are, yes, converted into high affinity state. So it will love to bind sodium, and as it is open inside, so it will take the sodium from in. So this is sodium loading stage. So sodium will bind here, another sodium here. How many sodium? 3 sodium, another sodium here, right? Now from step 1, now it has gone to the step number 2, but still it is in which state? E1, right? So we can say, what is this stage? E1 state plus ATP plus three sodium ions. So we will call this phase ATP loaded E1, ATP and sodium loaded E1, right? ATP and now it has to kick on the ass of sodium to get them out. But the situation is this, it shouldn't kick now, because rather than going out, it may fall in. So first it should close this point. So in next stage, what's going to happen, that E1, it will be still in E1, but Sodium is bound over here. Sodium 1, sodium 2 and sodium 3. But the real change is this point. These 2 points approximate each other, so that before they kick on the back of the sodium to expel out, they should close the or occlude the inner gate of the channel, so that sodium does not wrongly go back inside. So this is the point. This configuration, this is called still E1 but occluded, and of course it is still having ATP. So what will be this stage called? E1 ATP, E1 state with ATP plus, yes, 3 sodium, yes, and internally occluded, and so we have seen 3 steps. Again I will repeat it. Look at here. This is the pump. This is which configuration? E1. It is open inside. Step number 1, what is this? ATP bind. Step number 2, what will bind here? Sodium. Step number 3, occlude. Is that right? Once sodium is trapped in, some blast of energy should happen. Kick on the ass of the sodium, open the gate outside, and sodium should be expelled. Right? While we are moving forward, again I will repeat here, what were these sites binding for? Sodium. And here are the binding for potassium. Binding for potassium. In E1 state, affinity for the sodium binding state is high. First ATP bind, then sodium binding state sites affinity becomes high, then sodium will bind over there. After that it will occlude. Now it has to pump the energy. Now it has to pump the energy, and to pump the energy it has to break down what? ATP. So for this purpose a special domain will come into action. A special domain which was already there, right? This domain is called ATPase. Now this domain will kick over here, and ADP will be removed, and whole enzyme configuration will be energized, because when terminal phosphate bond of ATP break down, there is release of biological energy, metabolic energy. That energy is transferred to this pump, right? So I will make it a little smaller. So what will happen? Take it like this. Yes, what is here? Sodium into sodium pockets, and potassium pockets are empty. Is that right? And this pump, that is ATPase, has done its function, and when it has done its function, phosphate ADP has been released. ADP has been released, but one terminal phosphate is left over here, right? And this was the point, this was the hooker point where what was attached? ATP. There is another hooker point. This was the ATP binding point. This is phosphate binding point. So terminal phosphate is transferred to the next point. This is an aspartate. This is terminal phosphate. Again, it was having sodium binding sites, potassium binding site. It was having ATPase. It was having ATP binding site, and additionally it was having phosphate binding sites. So as soon as ADP removes, terminal phosphate is transferred to a special point which is called phosphorylation point. That is phosphorylation point. And now pump is phosphorylated. Now pump is phosphorylated. And once it is phosphorylated, it's getting the energy. As soon as it gets phosphorylated from E1, it will flip to the E2 state. From E1, E stands for enzyme conformation. E1 conformational state, as soon as it is phosphorylated, it will convert into E2 conformational state. So in this case, due to ATPase activity, it is flipping its conformation from E1 to E2, and in E2 its outer point is open, its outer mouth is open. So what I should write here, that now it is E1 phosphorylated. Here what is happening, E1 phosphorylated, of course it is still having 3 sodium. Here it is switching from E1 phosphorylated to E2 phosphorylated, right, where the affinity for sodium has become less, right. Let me repeat it from up to now. First of all, there are 3 clearly E1 states and then flipping state, and then there will be purely E2 states. Is that right? E1 state loaded with ATP, you tell me. E1 state, first of all, loaded with ATP. Number 2, bound the. Number 3, occluded. And number 4, phosphorylation and flipping. Now I will do and you will tell me. Yes, ATP binding, E1 ATP binding, E1 sodium binding, E1 occluded, and E1 phosphorylation flipping to E2 by breakdown of ATP into ADP and phosphate. Now when it goes into that, what is the next step? Next step is now it is still phosphorylated, am I right? E2 state is in which form? Phosphorylation form. And now as soon as it converts from E1 to E2, it opens its outer mouth and affinity of sodium pocket become less. So this is a stage of E1 where it is losing sodium losing state, right? We'll call it sodium losing state. So what is this stage? We say this is E2 phosphorylated state in which sodium 3 sodium losing 2 or expelling, right? Clear? What should be the next? Next is still now once sodium has been lost, its potassium binding sites undergo high affinity state. So what is this? E2 phosphorylating, E2 phosphorylated state with high affinity for potassium. So what should be this state called? E2 phosphorylated, 2 potassium loaded. Am I clear? Remember here, it was the phosphorylation which flipped E1 to E2. E1 was opening inside, E1 was sodium loaded state, and once it flipped, first it will lose the sodium, then it will gain the potassium, and as soon as it gets loaded with potassium, it will flip back to E1 with dephosphorylation. With dephosphorylation. So what is the next step? Oh, first occlusion. Yes, someone is right here. First of all, external point will undergo occlusion so that potassium does not escape out. So it is still phosphorylated. It is still phosphorylated. And what we will call it now? E2 phosphorylated, potassium loaded, externally occluded. Is that right? Externally occluded. This was what? E1 loaded with ATP. It was E1 loaded with plus, it was plus ATP. It was E1 plus ATP plus sodium, and this is E1, yes, ATP, yes, 3 sodium occluded inside, right? Then we come over here, flipping stage. We will say this is from E1 to E2 stage, during which, yes, what has happened? ATP breakdown into ADP plus phosphate, but this phosphate is present over here. Clear? Now sodium losing state, yes, E2 potassium gaining state, then external occluded state, right? And once it has externally occluded, I'm talking about this point. Once, now this is a point which has changed. External occluded. Here it was internal occluded after loading of sodium. Here is external occluding after loading of potassium. You guys are so intelligent. Good. Any question up to this? Now it should undergo dephosphorylation process. Now it should undergo dephosphorylation process. And as soon as it will dephosphorylate, it will flip from, yes, E2 back to the E1. That's great. From the E2, it will flip back to the E1. This is the state now in which externally it will remain occluded, right? And it was loaded with potassium, and when its conformation changes from E2 to E1, right? This is the point where it is losing from E2 to E1 while losing phosphate. So now this phosphate has been lost. So this is the dephosphorylation process which flips the E2 state into E1. Here it was phosphorylation process, right? Here it was phosphorylation process which was flipping E1 into E2. Is that right? Now here, as soon as it loses the phosphate, its inner mouth open, and its affinity for potassium becomes less, right? Dephosphorylation and its affinity for the potassium becomes less, and this becomes potassium losing state. Right? Now, how many steps have been done? First, ATP binding, E1 ATP binding, then E1 ATP and sodium binding, then E1 ATP with sodium binding and inner occluding, then ATPase activity of the enzyme breaking the ATP into ADP and phosphorylating its special residue which flips it from E1 to E2 and outer mouth open. Then in E2 state, phosphorylated E2 state, which is phosphorylated, affinity for the sodium becomes less and sodium is expelled. Then in the same E2 phosphorylated state, affinity for the potassium binding sites becomes high and potassium is bound. After that, E2 phosphorylated occluded, right? Then dephosphorylation and switching from E2 to E1. Just remember, dephosphorylation and switching from E2 to E1, right? And now at this very moment, affinity for potassium has become less. So I will write it here, E2, yes, here it is phosphorylation, dephosphorylation, E2 losing, I should say, look, E2 phosphorylated with 2 potassium, all of this going into E2 dephosphorylation. What is this? Phosphate is down with 2 potassium. Very good, it is E1, you are very right. So it means you guys are really learning faster than me, great. So this is flipping from E2 state, which was phosphorylated, lost the phosphorylation and convert into E1. And as soon as it convert into E1, what should be the next state? Losing the potassium and then gaining the ATP. Now it will, yes, lose potassium. It is dephosphorylated state. As soon as it loses the potassium, what it will get? ATP, and it will get the ATP here. Now, and then cycle will restart, right? Now you guys have to tell, what is this configuration? E1, and what is this configuration? That's loudly. Okay, E1 ATP loaded, then E1 sodium loaded, then E1 occluded, then ATPase action and flipping of E1 into 2 with phosphorylation, then loss of ability to hold, loss of affinity for sodium, losing the sodium, and then gaining the potassium, and after that external occluding. Did we talk about internal occluding? Yes. Now external occluding, and after that dephosphorylation and losing the potassium N and again gaining the ATP. Okay. Now someone needs to come here. Okay, you will come here. Okay, you can come here. Yes, doctor, you can come here. You are shy of camera? No? So please come here. Now we'll repeat this. Okay. You make your hands like this. No, like this. Right. So this is our sodium potassium pump, right? Which component? Beta or alpha? Alpha. Right. First of all, I bind here something. What is it? So E1 with ATP. Then I bind here sodium, E1 ATP and sodium. Then internally occluded. Then ADP release, ATP broken, ADP release, phosphate bound with the spartate unit, and now this is phosphorylated, which switch from E1 to E2 state, from E1 to E2 state. Next, losing sodium, gaining potassium, external occluding, and then dephosphorylation and flipping from E2 to E1, losing potassium, and then again gaining ATP, then again gaining sodium, yes, then internal occluding, then ATPase activity, phosphorylation, flipping, losing sodium, gaining potassium, external occlusion, and dephosphorylation and opening again. Thank you very much, doctor. Okay, let's have a break. After this, we will be talking about that this pump, how it is regulated by certain factors. Up to now, I only told that how it is binding the sodium, binding the ATP, binding the sodium, getting phosphorylated, transferring the sodium out, binding the potassium, and bringing the potassium in, and cycle repeating. So again remember, E1, ATP binding, sodium binding, then internal occluding, then phosphorylation and ATP breakdown phosphorylation, and E2 losing sodium, gaining external occlusion, yes, dephosphorylation, releasing potassium, gaining ATP, and cycle repeated. In the next section, we will be talking about what are the factors which regulate the number of pump in a cell and function of the pump, rate of functioning of the pump, because sodium potassium ATPase activity in a given cell can be altered by increasing or decreasing its number of pumps. Increasing the number of pumps by genetic machinery is activated to synthesize more pump, or decreasing the pump activity by decreasing the number of pump by inhibiting the genes which produce sodium potassium ATPase. This is one way that you alter the sodium potassium ATPase activity in a given group of cells by altering the presence of total number of pumps per cell. Another way is altering the phosphorylation and dephosphorylation of the pump and changing its function, right? So there are many factors which regulate the sodium potassium ATPase functions, like thyroid hormones, like aldosterone, like insulin, like dopamine, right? So after the break, we'll talk about how, yes, how thyroid hormone, aldosterone, and insulin increase the sodium potassium ATPase action, and how dopamine working through its D1 receptor decrease the sodium potassium ATPase activity, and what are the clinical importance of these regulation of the pump. Let's have a break.